All right, hello everyone. So, last time, we saw what were linear differential equations, and we saw their homogeneous version. The right side is going to be zero. Linear equation in general have um, coefficients of as functions of x. Okay, wherever you have something that's derived from the dependent variable. All right, the homogeneous one, the right side necessarily has to be zero. The linear expression, involving the dependent variable and its derivatives, the right side, it has to be equal to zero. And at the end, I talked about what happens when we had another condition when the linear homogeneous differential equation has constant coefficients. That just means that our derivatives have constant coefficients. Those functions of x which are coefficients of these, they have to be constants. All right. So this is the class of differential equations that we're gonna work with for a while, and specifically just to start things off in a simple manner, we're gonna deal with second order linear homogeneous differential equation with constant coefficients. The second order are gonna deal with the second order. And actually, there's one thing that I noticed for some reason, for some weird reason, whenever I wrote homogeneous in the last video, I forgot the E there. I really don't know why. Okay, so probably because the E is usually silent when we pronounce it. Anyways, so we're gonna deal with the second order version of this. So that's just gonna be let's see. We have y double prime, we have y prime, and we have y, and all of that is gonna be equal to zero. Now, obviously, these are gonna have coefficients, but as I said, the coefficients have to be some constants. Okay, and I'll call them for y double prime, I'll call it a. For y prime, I'll call it b, and for y, I'll call it c. And you might be able to guess, but the reason why I'm calling these, other than them just being the first letters of the alphabet, is just to kind of match it with the quadratic formula. And there's, you'll see more of a relevance to that just in a bit. So, anyways, this is my second order linear homogeneous differential equation, and it has constant coefficients. As you can see, a, b, and c are constants, and we'll also impose that a is not equal to zero. All right. So how do we solve this? Can we find a solution? And for that, actually, I'd like to try some things. But before that, I'd like to actually write this equation in a certain way, which personally, a while back, I personally didn't like this way of writing, to be honest. But I see that at least for kind of breaking the ice on this topic, this notation is kind of really useful. And the one I'm talking about is, as we talked about before, y double prime. We can write this as d2y. Okay, y prime we can write this as dy, and y is obviously just y. And so this equation is gonna be c y. You have a b here, and you have an a here. And all of that is equal to zero. Now, again, I'm saying one thing. This is not gonna. This is not the real situation. You cannot actually do this, but you can kind of think like you have y here, you have y here, you have y here. You can kind of think of factoring the y. And I'm again saying that this is not actually something valid. And even in the notation, it's really just a notation. It doesn't really mean that you're allowed to factor the y, but it's just a notation, which the advantage of which is, we can just write this a bit shortly. You can kind of think of factoring the y, okay, and what you'll have is something that looks like this. Again, all I'm saying is this is just a notation for this equation, okay. You cannot actually factor the y from the derivatives, okay. It's just a way of writing it. All right, but I actually found this, interestingly, I found this kind of helpful to introduce our solution, break the ice on this topic. So, what I'd like you to think about is something like this. So, you have this equation. Wouldn't it be convenient if suppose, say, you pick some function, some solution. We're gonna test some solution. Y, so y equals f of x. So we're gonna test that as a solution. All right. wouldn't it be convenient if, actually, I'll just write y. I'll just write y. Okay. So I'm going to test some y, okay, and I want that to be the solution. Wouldn't it be convenient? Okay, so this is obviously c multiplied by y. This one, you're taking the first derivative here, and you have a constant here. Okay, suppose say the first derivative, whether you write it like this or this, whatever it is, wouldn't it be really nice if this were just some constant, okay, some constant multiplied by your y, okay, multiplied by your y, something like this. Okay, so and also actually, yeah, right now this might not be that clear, but I'll just explain this in a bit. And also, if suppose say your second derivative, okay, just suppose that these are true, your second derivative or y double prime is gonna be equal to, again, we're gonna differentiate this. We're gonna differentiate your first derivative with respect to x. So I said that if you differentiate y, you're gonna get some constant m multiplied by y. So if you do that again, y gets differentiated again. M is just a constant, so that's gonna be left out, right? So m into m multiplied by my, right? M multiplied by my. That's gonna be your second derivative. M squared y. And the reason why I'm interested in some function like this, okay, why it seems convenient, is because if you plug this in here, okay, if you plug this in here, what you are gonna get is something like this. So I'll write it. I'll write it on the right side. So scroll back and forth. So you have a multiplied by your second derivative. Okay, but this is actually one advantage of the notation. Doesn't this equation, if you just think about um, d as a constant, okay, if you think about d as a constant, it's not, again, but just momentarily, if you think about it as a constant, this is a quadratic equation, right? This is a quadratic equation, and so if we want to solve this differential equation of ours, if you think about this as a quadratic, okay, this could, you could just easily solve it by finding the solutions to the quadratic, right? Finding the solutions to the quadratic. Uh, that's actually, the reason I'm interested in some function which whenever you differentiate it, all that you need to do is multiply by some constant m. You could even say some parameter. But anyways, I won't use that word that much. Some constant m. Just every time you differentiate, that's something that I'm looking for. Okay, is because if I have that, it really matches the pattern here. You can, instead of these d squareds, what you're gonna have is something like this. Actually, I'll actually use this one. Okay, go from here, and I'll just substitute those differentials of ours, so derivatives of ours. So a multiplied by second derivative, so a multiplied by m squared y, a multiplied by m squared y. Then you have b multiplied by the first derivatives, b multiplied by my plus c multiplied by just y. So this is equal to 0. And now you can actually factor the y. Okay, that's actually allowed. If you do factor it, what you get is am squared plus bm plus c y equal to 0. So I think now you should be able to see the link between these. I don't know how much this notation analogy was helpful, but at the very least, I hope now you can see what I'm trying to get at. What I want, is for us to be able to, although this is not a quadratic, and again, you cannot actually factor y. This is just a notation. But if it were like that, if it were actually a quadratic, and you were able to, suppose, say, factor the y, okay, this equation, this second order linear homogeneous differential equation with constant coefficients would actually be very easy to solve. You just need to solve the quadratic equation, right? You just need to solve the quadratic equation, and for that we are searching for some function such that every time you differentiate it, you just need to multiply by some constant m, okay? And if you have that, what the advantage there is, in this quadratic, what I'm calling a quadratic, the d squareds just get, the d's just get replaced by m's. Okay, same thing. Still have a quadratic, so the d's just get replaced by m, as you can see here. It's the same thing. Y got factored for real this time. Okay, but yeah, this is really what we're looking for. We want a quadratic here so that it can easily solve this equation. So now the question is, I hope you have got it until this much. I don't know how useful that analogy was. Anyways, so the thing is, we are searching for some function that meets this criteria. Now, can we think of some function that every time we differentiate, we just need to multiply by some constant, some constant that's inside the function, I guess. And if you just think about it just a bit hard enough, you would find that function. We have been dealing with that, I think, for quite a while. It's the exponential function, particularly something of the form y is equal to e to the power mx. Okay, so this one right here, this does actually meet our criteria, because if you differentiate this, you get m multiplied by e to the mx. Okay, or e to the mx, as it's y, m multiplied by y. In the second derivative, you differentiate that again. M is just constant, so you can leave that outside. So m multiplied by my, it's again, the reason why I selected this function is obviously because just to meet my criteria. So obviously, I'm gonna see the same behavior as just as what I just talked about a while ago. So my second derivative is gonna be m squared y. It's gonna be m squared y, right? And that's pretty easy to see. Differentiate that, just an m comes out, so m into m, so m squared exactly matches my criteria. And the benefit of that is, it kind of now we can actually, for real, as we see here, we'd have a quadratic. If you substitute the y's and the derivatives of y, as we saw, if our function meets this criteria, which it does, we will have something like this on our hands. Y is factored out. Okay, y is factored out, and you have a quadratic here, and this should be pretty easy to solve. We just need to solve the quadratic to to kind of get a solution. Now we'll actually proceed with that. Let's see what happens if we solve the quadratic and whatnot. So thing is, what we have here is, if you substitute y and its derivatives, is exactly as we saw, am squared plus bm plus c. This is multiplied by y, but y is equal to, as we know, y is equal to e to the power mx. Now this is equal to 0, and so if we want to solve this, it's actually super convenient. Again, another advantage of I guess you could say it's a bonus of the fact that our function is the exponential function. This can at least for real numbers, and except here, if you're using plus or minus infinity, actually this can actually never equal 0, right? This can actually never equal 0. So if that's the case, we can actually just divide both sides by e to the power mx. Only this part can be 0, right? Only this part can be 0 to solve our equation. So what we have right here is am squared plus bm plus c is gonna equal 0. Okay, if we do really want to find any solution to the differential equation. Now this is pretty interesting. I wanted to think about a bit, what we have done so far. All that we did is, we took our second order linear homogeneous differential equation with constant coefficients. We just talked about, it would be convenient if, like this notation, we were actually able to have a quadratic here, then y factored out, so we can solve the quadratic, and then we can proceed forward with finding some solution. And we actually were able to achieve that. Okay, we actually were able to achieve that by finding a function which is e to the power mx, y equals e to the power some constant m, okay, and x. So that function does meet our criteria, which we just spoke about here. And if it does, as we showed, we do have something like this. We do have something like this on our hands, where legitimately we have a quadratic, and multiplied by our function y, that's going to equal 0. And as you see, because it's e to the power mx, that cancels out, and uh, this is the main thing. This is the main thing. Our solution, okay, basically our solution to the quadratic, not the quadratic, our solution to the differential equation relies on the fact that for the fact that we can actually find solutions for this, or it depends on whether we can find solutions for this quadratic. Okay, everything is now on the shoulders of this one quadratic, and because this quadratic is so important, we actually call this, we give it a very heavy name. It's called the characteristic equation of our differential equation. That second order linear homogeneous differential equation with constant coefficients, it's really becoming tiring saying that over and over again. But for that, this quadratic right here is called the characteristic equation of that differential equation. It's called the characteristic equation because finding the solution to that is dependent, and to be honest, solely dependent on the fact that we can actually find solutions for this. Alright, that's why it's called the characteristic. And again, it's also called the auxiliary equation. So I'll just write that down. The characteristic one, and the characteristic is more common though. Anyways, so we have a quadratic, and as we said, given a is not equal to 0, we can actually solve any quadratic, right? We have factoring, and in general we have the quadratic formula. Definitely we can always find solutions for quadratic, right? So that's actually pretty neat. That we indeed will have solutions. Suppose say quadratic, so we should have two solutions. And again, there are some things that I'll talk about at the end. Just bear with me for now. I'm sure a lot of you are thinking about some particular thing, and I'll talk about them in a bit. But I don't want to ruin something. Ruin the flow that we have now. So we should have two solutions. Let's call that M1. Let's call those M1 and M2. Okay, let's call those M1 and M2. Yeah, that should be fine. So if we have these two solutions, then we said that y equals m of x. It's gonna be we're testing it to be the solution, and what we see is it will be a solution if we have if we can find solutions to this. And as I said, we can, because it's a quadratic. Any quadratic will have solutions according to the quadratic formula. So the solutions are M1 and M2. M1 and M2. That means that M1 and M2, if we substitute them, we'd have to do that separately. But if we substitute those, they will actually give solutions, right? They will actually give solutions to our differential equation. So what I mean is since M1 and M2 are solutions to a quadratic, it also means that y equals e to the power m1x. I'm just substituting that. Okay, this is gonna be a solution. To my quadratic. It's not my quadratic, my differential equation. Again, same thing with m2. Y equals m2 of x. Not m2 of x. Y equals m2x. Wait, what am I saying? Really? Whoops. Y equals e to the power m2x. Y equals e to the. That's another solution. Okay. So these two are two solutions. To my second order linear homogeneous differential equations coefficients. Now there's actually something really interesting happening. We have, as you can see, we have two solutions. But the thing is, it's not general, and the reason is neither of these are general, because it's actually, I'd like you to realize one fact, that M1 and M2 are not unknowns. Okay, given that we know A, B, and C. Okay, so given that our differential equation is completely clear and all, that we can see the coefficients aren't unknowns or anything. M1 and M2, we can find their values. They're not unknowns. Okay, they are known values. Okay, so there are actually no unknowns in either of these solutions. Okay, and as a general solution to any second order differential equation, it should have two unknowns, right? Particularly it should require two subsidiary conditions to get a particular solution. But if we need two conditions. We need two conditions, and also that does mean that we should have two constants, right? We should have two constants. We should have two constants, or arbitrary constants. So that a general solution should have two arbitrary constants. Because the order of the differential equation is 2, but we don't see any arbitrary constants right here, right? We don't see any arbitrary constants right here. So none of those are the general solution. But we just talked about these being solutions, so we can actually use that property that we discussed in the last video of homogeneous equations in general, linear homogeneous equations in general, that if we have two solutions, and actually if we have, how many solutions there are, a bunch of solutions, any linear combination of those solutions, and this is a linear combination, just multiply some arbitrary constant with one of your functions, some arbitrary constant with, the other, any other function, all your solutions, you multiply them by some arbitrary constant, and then you just take the sum of those. So that's called a linear combination of functions. So any linear combination of my solution functions is also gonna be a solution. Okay, we proved that theorem for linear homogeneous equation. This is one. In fact, this has constant coefficients, so an even narrower class. So, anyways, this should be valid here. If we have one solution right here, we have one solution, we have another solution, we can actually say that this is going to be a solution. If we form a linear combination of these two functions, of these two solution functions, we should have a solution on our hands. So let's actually try to form that. C1 multiplied by one of my functions, so e to the power m1x, okay, plus c2 multiplied by the other solution function, so e to the power m2x. Voila, this has to be a solution. As I said, this has to be a solution. And what's really important, what's key here, is this has two arbitrary unknown constants. Right? This has two arbitrary general or unknown, whatever you want to call them. This has two unknown constants, arbitrary constants, right? And that is why this is the general solution. This has to be the general solution of my second order linear homogeneous differential equation constant coefficient. So this is the general solution, okay, to my second order linear homogeneous differential equation. So I'll just recap this. So all in general, if we want to solve an equation like that, and I'm kind of getting tired saying this over and over again, but what we need to do is our solution is gonna have the form just as a test function, it's gonna have the form e to the power mx. But anyways, the main thing is we take our our differential equation, replace the derivatives, okay, the derivatives of y and y itself with some constant, okay, with some unknown constant or variable, to be honest, which we need to solve for. So we're calling that m. But anyways, thing is, the easiest way to form your characteristic equation is what I'm trying to get at. Each one of these you just replace by the corresponding power of f. So m. So you have the second derivative, you replace that by m squared. First derivative, you replace that by m to the power 1, or just m. And zeroth derivative, you replace by m to the power 0, or just 1. To be honest, you don't really need to put anything here. C will just be by itself. So that's basically what I'm getting at. This is you take your second differential equation, you take your second order linear homogeneous differential equation constant coefficients, you replace the derivatives y with the powers of m, your constant that, or constant that you need to solve for. You solve for it, you get you should get two solutions, and then you plug them in, then you plug them in here. You just plug them in here, okay, to get your general solution. Now, finally, I'll actually address the elephant in the room, you could say. It is a fact that I'm pretty sure a lot of you have already seen through this, or are wondering about this, it's not necessary for us to always get two solutions. It's a fact that it's a quadratic, so it can have repeated solutions, something like m squared minus 2m minus 1. If our differential equation was y double prime minus 2y prime plus 1 equals 0, our characteristic equation is gonna be this. This has only one solution, m is equal to 1. So what do we do, in that case? What do you do in that case? And also the fact that, that's again another intriguing and worrying thing, you could say, is, our characteristic equation can have complex solutions, right? Can have complex solutions. So what are we gonna do there? We to be honest, don't really want complex numbers coming into our real number differential equations. So what are you gonna do then, and all that stuff? So those things, basically what I'm saying is, I'm pretty sure I've seen this before. Of a quadratic equation, you have three cases, right, for the solutions. And I'll talk about what happens in those three cases. Two distinct roots, you have only one repeated root, or you have two complex roots. I'll talk about what happens in those cases, and example problems with those, okay, and all that stuff in the next three videos. Okay, today I want to just end it here. Okay, and I know, but we at least would like to take away the fact that this should be my general solution. And to be honest, I'll already break it to you, but for the case that we have a single solution, we kind of have to modify it a bit, okay, quite a bit, to be honest. So anyways, all that stuff we'll talk about the next few videos. So see you then, see you later. And if you appreciated the video, if you found this helpful, please do leave a like, subscribe, and yeah, I'll see you next time, and study smart.